Hello, here is an application for angular and linear velocity. Okay, you may go through my video where we have developed a relation between the two, right? So basic concept was that if there is a wheel, right, then let us say that a point on a wheel makes one full circle. So in that time, it rotates through an angle of 2 pi radians, correct? So it is like rotating 2 pi radians, that gives rise to the angular velocity. But in the meanwhile, it covers the distance of circumference, which is 2 pi r. And you can consider this point to translate linearly this distance. So during the time when a wheel makes one full circle, then it covers the distance of 2 pi angular rotation and translates 2 pi r distance horizontally, and that brings us to a relation between the two distances in the same time, right? So the two velocities are connected. The relation between them is v equals to omega r, where v is a linear velocity, omega is the angular velocity, and r is the radius of this wheel or the circular path which is under consideration. Okay, so full derivation, you look into the video how we derived linear velocity is angular velocity times radius, but that's kind of constant. You see 2 pi is angle covered times r. It makes sense. Do you see that? Both, if you divide by time, you get rate of change of angle on one side, which is 2 pi by t. Do you understand? So on one side, angular velocity would be rate of change of angle, and the angle is 2 pi, right? So 2 pi by t, and on the other side, it is 2 pi r by t. You know, same time, this point actually moves 2 pi r distance, which can be translated linearly here, right? So this is the component of our angular velocity, and this is the component of our linear velocity. The only difference you can find them is that this angular velocity and this linear velocity have this r, right? So v is omega times r. If I multiply omega by r, I get this. Do you see that? And that's a very simple and straightforward way of relating the two, correct? So let's now read the problem and try to solve it. A wheel rotates with angular velocity of 10 revolutions per minute. Now here, we normally give you angular velocity in revolutions per minute. We got to change it into radians per minute or radians per second. That's first part. If the radius is 15, find the linear velocity. So we know the radius, we know r, right? So we know r is 15, but we need to find omega in revolutions per minute. Instead of revolutions, we need radians, right? So we'll do that. So we say omega, the angular velocity is 10, and we say, I'll show you another way of converting the units, is revolutions per minute, correct? Now, in one particular revolutions, how much radians do you go? So when we make one revolution, we do 2 pi radians, right? So we say 10, and one revolution, let's say this is revolutions per minute, and we say 2 pi radians, right? 2 pi radians, and in one revolution, right? So if you see, it's a very easy way of converting units. So revolutions get cancelled, and we get radians per minute. You see that? So we have omega as 2 pi into 10, which is 20 pi radians per minute, right? Now this radians per minute can be converted to seconds, right? So in that case, 1 minute, we are get rid of this minute, and instead we want seconds, right? 50 seconds, correct? So once we do that, minute and minute will cancel out, and we get 20 by 60, which is 1 over 3, or pi by 3 radians per second. Do you see that? So this is a very simple and straightforward way of converting units from, we see how easily we converted revolutions per minute to radians per second. Strictly speaking, radian is just a ratio. It's not like centimeter, meter, or something else. It's just a ratio. It's a ratio of arc length to radius, right? And now we can find velocity. Since we know radius is 15 for us, right? We know radius is 15. So velocity is omega times radius. Omega is pi by 3. And let me write units. Radian per second. And we have radius of 15 centimeter, right? Correct. Now, if you do that, we have velocity. If you want to write velocity in meters per second, then we need to convert the centimeters to meters, right? So let's do that. So we have 15 will give us 3 divided by 15 gives 5, right? So we get 5 pi centimeters per second we can write here, because strictly speaking radian is not exactly a unit. It's a way of saying that we are still dealing with angular things, right? Somehow the angle component theta is there in it. And we have centimeters per second. To convert to meters, we know 1 meter is how many centimeters? 100, right? 100 centimeter. So we can have this, and we can divide this by 100. So we get 0.05 pi meters per second, right? So because a centimeter gets cancelled off now. Now if you need answer to 2 or 3 decimal places, you can always use your calculator and say 0.05 times pi, which is 3.14 for most calculations, and we get 0.157 meters per second. Now, so that's our answer for the time being, right? So I hope you understand how we have done it, and that's a very simple way of doing converting angular velocity, or such a problem, linking angular velocity to linear velocity. Okay, so what did we do basically? We know that linear velocity is angular velocity times radius. I made an attempt to show you how, to give you a very big picture of it. It's a very clear and it's a very beautiful concept if you see it. So rate of change of angle is equals to rate of change of distance. Okay, the central angle changes in one revolution by 2 pi, and linearly it covers a distance of 2 pi r. So velocity will be distance covered, or the angle changed, divided by time. So which gives rise to omega and v. If you look at the equations, the only difference is of r. So v can be written as, from here, if I do omega dot r, then I get what v is, right? So that's how we can derive our relation. So we use this relation here. It has been derived in another video. You can look into that. Now here the omega was 10 revolutions per minute. We converted that to radians per second and then multiplied by 15 centimeters. We could have converted centimeters to meters straight away here, 0.15, and then got our answer to exact value or to decimal places as required. I hope you appreciate the way we have done, and you understand the concept that both angular and linear velocities are very much related and very easy to work with. Thank you.